Alright, so here's the document camera portion of this lecture. And I'm first just going to redraw what I had on that second to last slide there, which is a normal sampling distribution for means. So it's normally distributed, which means it has this nice bell shape. On the x-axis, we have the possible sample means that we could get. So remember, these are the possible means that you could get when you take a sample, and then the probability of getting each one. So our most likely values are clumped around our overall mean, which we're calling mu sub x bar, and our standard deviation is given as sigma sub x bar. The overall mean for our sampling distribution is equal to the mean for a variable, whatever it might be. The standard error for our sampling distribution here, aka its standard deviation, is going to be found using the standard error formula. I know you've all been on the edge of your seats waiting for this, but it looks like this, where this is the standard deviation for your variable, and n is your sample size. And just for completion, I'll say this is your population mean. So this is your population standard deviation. Your, I can't tell if there's actually an E here. Okay, your sample size. And so to find the standard error for our sampling distribution of means, we're just going to divide our population standard deviation by the square root of our sample size. So I'm going to go through an example here using the same normal distribution that we had last week to talk about probabilities. And we're going to say that we're looking at the number of thefts likely to happen over the course of a month in a chain of box stores. So we're going to call it StatSmart, and we're going to assume that there's a whole bunch of these in the country. And we said before that over the course of a month, our variable was the number of thefts that's likely to occur. The most likely number of thefts was 65, and then it's normally distributed, so way more than 65 is unlikely, way less than 65 is unlikely, and we had these population parameters. So our mean is 65, our most likely value, and then our standard deviation was 15. So the standard deviation, again, just describes how narrow or how spread out your normal distribution is. So we're going to say, for the purposes of this example, that we're going to take a sample of 30 StatSmarts. And this is a normally distributed variable, so it actually doesn't matter what our sample size is here. Our sampling distribution of means is going to be normal regardless, because we're starting with a normally distributed variable. But if your variable that you start with is not normally distributed, as long as you have a sample size greater than 30, you're going to have a normal distribution for your sampling distribution. And we're interested in what the mean number of thefts might be in our sample of 30 StatSmarts. So we want to know, if we take a sample of 30 of these stores where this describes how the number of items that's likely to be stolen, what is our sample mean likely to be? So what we need to do to fill this out is come up with a probability distribution that describes the different possible sample means that we could get and the probability of getting each one. So here the variable on our x-axis is going to be the mean number of thefts, or x bar. So we're going to take a sample of 30 of these stores, and we want to know in the sample of 30 stores, what are the possible sample means that we could get? Assuming that there's lots and lots of these StatSmarts across the country, and they all have probability distributions for thefts that look like this. So again, we know that the sampling distribution is going to be normally distributed. So we can start by drawing it out like this, and we're going to have probability on the y-axis. So the first thing that we want to fill in our sampling distribution is the overall mean, or mu sub x bar. This is the easy one. So this is the one that is always going to just be equal to your population mean. So in this case, or your probability distribution mean. Those things are essentially interchangeable for these purposes. So in this case, our population mean for this variable is the mean of our probability distribution, and it's equal to 65. So the overall mean of our sampling distribution, or mu sub x bar, is going to be equal to mu, which we know is equal to 65. So this one's just going to be equal to 65 as well. This means that in our sample of 30 stat smarts, the most likely sample mean that we're going to get is equal to 65. But we still need to know the standard error for our sampling distribution. And to calculate the standard error, we need to use the standard error formula here. So our standard error is going to be given to us by our population standard deviation and the square root of n, or the sample size. So here we're just going to look at our population probability distribution again. We're going to see that our standard deviation is 15. So we'll plug in 15 for sigma here. And our sample size is given in this part of the problem, and it's 30. So with a sample of 30 stat smarts and a population standard deviation of 15, we can calculate the standard error for our sampling distribution. And if we do this, it's going to come out to 2.74. And what we're left with is a normal distribution with a mean and a standard deviation, aka standard error. And once we know those two things about a normal distribution, you can do anything with it that you would do with any other normal distribution. But before I go through some examples of that, I do want to just quickly note again the relationship between sample size and standard error. Because we are dividing by the sample size here, square root of the sample size, the bigger this number is, the smaller your standard error is going to be. So if you had a sample of 300 stat smarts, you'd be dividing by the square root of 300, and you'd end up with a much smaller standard error. So in other words, your most likely sample means would be much closer to your population mean. So in other words, your sample would be more likely to resemble the population. All right, so let's look at some examples of things that we can do with this. Well, one thing you can do is apply the empirical rule. And as we learned last week, the empirical rule tells you the proportion of outcomes under the curve within 1, 2, and 3 standard deviations of your mean. When working with the sampling distribution, you can use it in the same way, and it'll tell you the proportion of outcomes within 1, 2, and 3 standard errors of your overall mean. And those things, just like they did in the other normal distribution, tell you the probability of getting a sample mean within that range. So as an example here, I'll use the first part of the empirical rule that tells us that within 1 standard error, so within 1 standard error of the mean, where you're either going 1 standard error jump in a positive direction or 1 standard error jump in a negative direction, we know that we're going to find 68.3% of our area under the curve, or a 68.3% probability of getting some outcome within this range here. So what we can do is, just like we did last week, to find out the values that include, 68.3% of the area under the curve around the mean, we're just going to add our standard deviation and subtract our standard deviation from our mean. So we had standard error, not standard deviation. So I'm going to write this out just so that you guys can see it while I talk. So we have an overall mean for our sampling distribution of 65, and we have a standard error for our sampling distribution of 2.74, where this is the mean number of thefts, and this is the probability of getting different possible mean numbers of thefts. So to find out our one standard error in a positive direction, we're going to add our standard error of 2.74 to 65. So we're going to do 65 plus 2.74, and that's going to give us 67.74. So this is 67.74 here. To find our overall mean minus the standard error, we're just going to do 65 minus 2.74. And that's going to give us 62.26. And so these values, again, are just jumps of one standard error in a positive direction and one standard error in a negative direction from the mean. The empirical rule tells us that within one standard deviation of the mean of a normal distribution, or in this case within one standard error of the overall mean of our normal distribution, we're going to find 68.3% of the area under the curve. This corresponds to the probability of getting an outcome between these two values. So using the empirical rule, we'd be able to say that there is a 68.3% chance that if you take a sample of 30 stores, you're going to get a sample mean between 62.26 and 67.74. So we'll say in a sample of 30 stores, there's a 68.3% chance of obtaining a sample mean. So here the outcome we're talking about is the sample mean between 62.26 and 67.74 thefts. So pretty similar to what we did last week. The only difference here is that instead of looking at a probability distribution for a single variable, we're looking at a sampling distribution that tells us the probability of getting different possible sample means in the 30 stores that we're going to be looking at. And with this, you could do the same thing for 2 or 3 standard errors away from the mean as well. So you could apply the whole empirical rule. I'm not going to go through each one now because we did that last week and it kind of takes a while. But you could do the same thing here where you'd find 95.5% of your area under the curve within 2 standard errors, so 2 standard error jumps out, and you'd find 97.7% of your area under the, 99.7% of your area under the curve within 3 standard errors of your mean. So same idea. The only thing that's different again is that you have to calculate this standard error, and then you're looking at the mean instead of the variable values. Okay, so with that, I'm also going to go through a quick example of how you can use z-scores when dealing with a probability distribution as well. So a z-score, with a sampling distribution. So what a z-score tells you in a sampling distribution for means is how many standard errors away from the overall mean is a particular sample mean. So I'm going to just write that out. So how many standard errors for these guys from the overall mean, this guy, is a particular sample mean. So this should also look relatively familiar. When we talked about z-scores last week, we were talking about how many standard deviations away from the mean a particular variable value was. In this case, we're not looking at individual variable values, instead we're looking at sample means. So we were going to know how many standard errors away from the overall mean a particular sample mean is. And to do that, we're going to use a z-score formula for a sampling distribution. And you should also get deja vu when looking at this one, because it's almost the same as the z-score formula for a regular probability distribution. Again, the only thing that's different is that we're swapping out these values that apply to sampling distributions for the ones that would apply to a regular probability distribution. So our z-score formula for a sampling distribution looks like this. Where we have x bar referring to our sample mean, we're subtracting our overall mean of the sampling distribution, and we're dividing by the standard error of the sampling distribution. And with this formula, we can find a z-score for any possible sample mean that you could get. So as an example here, let's say we're interested in finding the z-score for 60 thefts. So we want to know in our sampling distribution of means, where we're looking at the possible sample means that you could get and the probability of each one, where, sorry, this is tiny, we have our overall mean of 65, we have our standard error of 2.74. We want to know how many standard errors away from the mean is a sample mean of 60 thefts. So again, when we find a z-score, what it's going to tell us is how many standard errors away from the mean is this. So we can plug in these values to our z-score formula to find the z-score for a sample mean of 60 thefts. And so we've got z here. We know that our sample mean is 60, so that's the value that we're looking for. We know that our overall mean of the sampling distribution is 65, so that's what we have up here. And we know that our standard error for the sampling distribution is 2.74. And that's what we calculated with the standard error formula on the last page. So we're going to divide by 2.74. Now you can do this math, and if you subtract 60 minus 65 and then divide by 2.74, you get a z-score of negative 1.82. So what this means is that a sample mean of 60 is negative 1.82 standard errors away from the mean in a negative direction. So 1.82 standard errors away from the mean in a negative direction in the sampling distribution. Okay, so why do we care about this? Well, when you're working with a normal distribution, you can use z-scores to find the probability of getting a sample statistic that is within this range. And you can do so using the z-table. In the exact same way that you would use the z-table if you were working with a probability distribution rather than a sampling distribution. So if you wanted to find the probability of getting a sample mean that was between 60 and 65 thefts, for example, you would use the z-table to find the area under the curve between these two values. And then that area would correspond to your probability. And the reason for this is that once you're working with z-scores, you're in a standard normal distribution where you have a mean of 0, a standard deviation of 1, and because it's all standardized and everything is counted in z-scores, you can use the z-table to find the area under the curve between those two values, because they'll be totally equivalent. So again, when you convert to z-scores, it no longer matters that you're working with the sampling distribution. You can treat it like any other normal distribution, use the standard normal distribution, and find the area under the curve between those values. And again, I'm not going to go through a ton of examples of how to do this because we did cover that in pretty good detail last week. But the idea is that once you calculate a z-score, you can use it exactly the same way as you used a z-score last week to find the area under the curve between two values. And so that's all I've got for you guys this week in talking about sampling distributions for means. As I hinted at earlier in the lecture, we're going to be applying these to do some more useful things in the upcoming lectures in this class. But for now, we'll leave off this part of the class before spring break with an introduction to them and what they are and how to work with them. So I hope you guys all have a great week. I won't be posting any lectures next week, but we'll be back to business as usual after spring break. So with that, I'll sign off, and I hope you guys have a great break.